So let's talk about another command. This next command lets you visualize transformational networks in this pitch class space. The command's name is net, standing for network. And after that, you write three numbers representing the trichord that you want to start at in this pitch class space. And then you apply a transformational series of operations to that trichord over and over and over again until you get back to the original trichord. And it will it'll connect to those trichords in space so that you can see how it moves through the space. I'm going to be using commas in this command, although in this one command the commas aren't necessary. It's useful for clarity. So net and then three numbers separated by spaces representing the trichord that you're going to start with, and then a comma, or not if you don't want the comma. And then now we write the transformation for each member of the set. And I'm going to do these. There's three types of transformations you can apply in this space. Let's just start with transposition. So I can write three numbers for each of the three members of the trichord, and at the end a semicolon. Remember, a semicolon tells the application that your statement is done. That's the end of the command. So what we're going to do is we're going to start with 0, 0, 0, and then we're going to transpose the first member by 0, the second one by 1 pitch class up in pitch class space, and then the third one going down, or -1, which would be the same as writing in an 11 in pitch class space. And it will apply that over and over again. You'll get to the second trichord, you'll apply that same transformation and keep going until you get back to the 0, 0, 0, 0, excuse me. So when we're done, press enter, and there it is. It grays out all the rest of the trichords in the space, and it draws, in this case, a diagonal line, starting with 0, 0, 0, up 1, down 1, up 1, down 1, up 1, down 1, all the way until we get back at 0, 0, 0 again. And you can see other lines in the space. Those are just duplicates over on the edge of where the space would wrap, where the space is wrapping, actually. So this is a straight line, and actually for transposition, if I just apply one transformation, I'll always get a straight line in the space. Let's do one more like that. Net 0, 0, 0 again, comma, and we'll keep this old transformational network in the space until we clear out the space, and I'll show you that in a second. 0, 0, 0, and now this time I'll do 2 to the first member, -1 to the second, and 0 to the third. And actually, let's do maybe 1 to the third. So it's going to transpose the first member up by 2 pitch classes, second one down by 1, and the third one up by 1, and it'll do that over and over again. And there's our second network. Starting with 0, 0, 0, and I'm actually looking at it backwards here. It's going this direction. So 2 for the x. Oh, and there's something that I didn't mention, which is useful. When you write out this command, it then iterates through the transformation and prints out each of the trichords in the network. So it shows we start. It doesn't print out the first one. We start at 0, 0, 0. It tells us the next one is 2, 11, 1, then 4, 10, 2, and 6, 9, 3, and so on. And then it tells me at the end how many transformations were necessary in order to get back around to the beginning, and different networks will have different amounts. These two that I chose have 12. If I want to do a slightly more complicated network, first let's clear the space so it's more easier for us to see the next network. For that, you write net clear. You had a show clear command to clear all of the shown trichords, and you have a net clear command to clear all the networks. That's so you can clear, if you have in the same space you're visualizing trichords through the show command and through the net command, you can clear one and not the other. So we've cleared it. Now let's do another network, 0, 0, 0 again, and this time I'll do 0, -1, 1, comma. Again, the commas aren't totally necessary, but I find them intuitive. And then 2, 0, -1. Okay, so what's going to happen now is it's going to start with 0, 0, 0, then it's going to transpose up by 0 for the first member, down by 1 for the second, up by 1 for the third, and then the result of that operation, this second part will be applied to that. So from that next trichord, 2 will be added to the first member, 0 to the second, and -1 to the third. And it will then go back to the first transformation, and then the second, and it'll alternate the first and the second until you get back around to 0. So it's a sequence of transformations that you're doing. Now if we press enter, you'll see, let's go back to 0, a jagged line. That's because we have a sequence, an alternating sequence of these transformations. So these will all create jagged lines, whereas the other operation that we did created straight line. And we've got all of these trichords printed out, and it tells us there are 24 transformations in this network. So I actually abbreviated this. Let me clear it again. I abbreviated this command. There are 3 types of operations, transformational operations: transposition, traditional inversion, and then inversion around an axis. And so there's a slightly different code for each of those. For transposition, you can either write a number and it automatically assumes that that number means transposition, or you can write the letter T and then without a space a number. So this is the kind of longhand way to do it for total clarity. T0, T-1, T2, and there it is. All right? So, or you don't have to write the T if you don't want. If you don't write any letter, it assumes you're talking about transposition. I'm going to clear this. Let's do another network starting with 0, 0, 0, and now we'll do traditional inversion. So I'll say I, that's the letter you need to use for inversion, and then I1, I3, I0. So that is as in traditional TNI operation, so we're inverting around 0 and then transposing. That's what's happening here. And this is also going to create a straight line. But interestingly, this is just 2 transformations, and actually I think probably all inversions with just 1 transformation in their sequence will do this. Goes to 1, 3, 0, and then it goes back to 0, 0, 0 again. That's why it doesn't go infinitely into space. So let's do another one. Clear this out. And let's do 0, 0, 0, I1, I2, I0, comma, I. Then we'll do a transformation, or a transposition. So one that's all inversion, one that's all transposition, and then alternating back and forth until we get back to the beginning. And this is just 4 that creates the network. And this would look slightly different if the space wasn't wrapping as it is now. So I'm going to turn off wrap space. Now we got to find the space, and there it is. So it looks a little bit different in the space now that we can't go across an axis threshold. All right, I'm going to turn wrapping space back on, wrap space on. There it is. You can see the difference. Okay, so a third type of transformation, as I mentioned, is inversion around an axis. Let me clear this out. And now I'll say net 0, 0, 0. For this, I use A for axis. So A0, A1, and then if I want the axis to be between, so A0 means invert around the 0, 6 axis. A1 would mean invert around the 1, 7 axis. And if I want to invert between 2 pitch classes, then I would say, let's say I want to invert between C sharp and D. I would write 1.5. So that's between the 1 and the 2, semicolon. And I'll do that. And there it is. This is also typical if I'm just doing one operation like this. Let's do, and it prints it out for me and shows me that there are 2 transformations. I'm going to clear this. And then let's do another one. 0, 0, 0, A1, A3.5, A2, comma, T1, I3, T, -1. Okay, so some compound transformational sequence with different types of transformations in the sequence. And that creates a nightmarishly complex network of only 12, but it's a little hard to see in the space. We could fly around to each of them. We do have all of the trichords listed here, and we could then slowly fly around. But with networks that are shaped like this in the space, sometimes it's easier to see it when the space is not wrapping. Sometimes it's not. Depends.